Hello, everybody. Welcome to this lecture here, first lecture in Unit 4. Today we're going to look at specifically waves and vibrations. This entire unit covers what is a wave and wave concepts, and then leads us into sound and light. So today we're going to focus on Chapter 20, or 20.1, but this whole entire little mini unit is going to cover 21, which are waves, wave motion in 20.2, and then wave interference and energy in 20.3. Today, by the end of this lecture, you should be able to understand and describe the difference is between a transverse and a longitudinal wave, and describe the parts of a transverse and longitudinal wave, along with be able to calculate the speed of a wave, knowing frequency and wavelength. So let's get started here. So we got to recognize waves are all around us. There are different types of waves. Waves carry energy. That energy typically carries information. So for instance, the stoplight here carries energy in the form of waves. It gives us information. Our eyes read the waves, and we can determine not only is there a light, but we can see different colors of light. Your cell phones, you grab your cell phone, you send a text or a phone call or a Snapchat or whatever it is that you do on your phone. Boom, it sends a wave signal out, and it goes from your phone to a tower to the person's phone that you've sent a message to, or you're calling or sending some type of social media response to. Sound carries waves. Right now you're listening to my voice talking. My voice is being recorded over through my computer, but then being saved here in this presentation, and then your device is then giving that sound off, which is then going into your ears, going down your eardrum, rattling your eardrum, banging into your cochlea, and your cochlea is reading those waves to hear the sound. Throwing a rock into water, boom, ripple effect, waves. We see that right there. On a windy day, you go out on a lake, you're going to see waves on that lake. So waves exist. Now, there are two types of waves. The first type of wave that we're going to talk about is a transverse wave. Now, the key thing that I'm going to talk about here with both types of waves is we need to understand what is the direction of motion and what is the direction of oscillation. Oscillation means the vibration. So in a transverse wave, the motion of the wave is horizontal, while the oscillation or vibration is vertical. So what that tells us how we state this now is a transverse wave is a wave where the wave motion is perpendicular to the wave oscillation. Waves on a lake when it's windy is a great example of that. Now, there are different parts to a wave, a transverse wave. So first off, imagine an imaginary line right here that I'm drawing with my cursor. Okay, that is the resting position. Now, this is a harmonic motion graph. Okay, transverse waves are harmonic motions. Okay, it creates a harmonic motion. It goes up and down, back and forth. The uppermost part of a wave is called the crest. The bottommost part of the wave is called a trough. The wavelength is the distance of one cycle. Typically, we measure one cycle from crest to crest or trough to trough because it's the easiest. Now, imagine that resting position. We already learned that the amplitude of a harmonic motion graph is the distance from the resting position to the top part, which we now know is the crest, or the resting position to the bottom part, which is now the trough. Okay, the second type of wave that we're going to discuss is a longitudinal wave. Now, a longitudinal wave is a wave where the motion of the wave is parallel to the oscillation or vibration of the wave. So the motion goes in one direction, the oscillation is going in the same direction, or can be going back at that, but on the same plane essentially. Here is an example of a longitudinal wave now with the parts labeled. First off, this is a compression. Now, anytime we have a longitudinal wave, particles will compress together and then they will spread apart. The compression is called a compression. The spread apart part is called a rarefaction. We measure the cycle of the wave from the end of a compression to the end of the next compression. Now, we're going to look at speed of a wave. Now, what we know is that the speed of the wave v is equal to frequency f times wavelength lambda. Lambda is the Greek symbol for wavelength. Now, speed is measured in meters per second. That's important when you're identifying it in problems. Frequency is measured in hertz. We already knew that. wavelength is measured in meters. Now, using my algebra skills, I'm able to manipulate the equation to solve for any of the three variables. As long as I know two of the variables, I can solve for the third. So speed is equal to frequency times wavelength. Frequency is equal to speed divided by wavelength, and wavelength is equal to speed divided by frequency. So we're going to do a couple problems here. I'm going to walk you through them so that you know how to do the worksheet that you're going to be doing on wave speed. So wave speed problem number 1 says if a wave travels with a frequency of 10 hertz and a wavelength of 2 meters, what is its speed? So first off, okay, we do not know speed. It says what is its speed? So right here by speed, I'm just going to put a question mark right there. That's going to be my variable x that I'm going to solve for. Now I'm going to find frequency and wavelength. Remember, frequency is in hertz, so 10 hertz. Wavelength is in meters, so 2 meters. Knowing those units is super important because that will help us. Now we don't know wavelength, or wave speed, sorry. We do know wavelength, that is 2 meters. So I'm going to go back to my equations. I'm going to find the equation for speed. I'm going to grab that equation, bring it to this problem. Lagging a little bit here, I apologize. I'm going to put it in. Now I'm just going to plug in my numbers. So frequency is 10 times wavelength, which is 2, which 2 times 10 is 20, and then speed is measured in meters per second. Okay? Go to problem 2. Problem 2 says if a wave has a speed of 300 meters per second and a wavelength of 25 meters, what is its frequency? First off, it says what is its frequency? So I know F is going to be my question mark. Now I'm looking for speed. I'm looking for meters per second. There it is, 300 meters per second. Wavelength is in meters. There it is, 25 meters, or M. Solve for my problem. Now I'm solving for F. Go to my equations. I have my equation for F. F is equal to V divided by wavelength, or lambda. Back here. Drop in my equation, plug the numbers in. So 300 is divided by 25, which is equal to 12. And now it's frequency, so I know that's hertz. Okay? Third problem now, and the last problem we're going to go through today, the last type. Okay, a water wave has a frequency of 0.25 hertz and has a wavelength or wave speed at 1 meters per second. Determine the wavelength of the wave. So I do not know wavelength. Looking for wave speed, meters per second. There it is, 1. Frequency, 0.25 hertz. Solve the problem. Looking for my equation for wavelength. You know, wavelength is speed divided by frequency. Plug my numbers in. Speed is 1 divided by 0.25, which I will get 4. And when I plug in my calculator, and now I'm wavelength is in meters. Okay? If you have questions on how to do those problems, please reach out to me. Lastly, we're going to talk about the last type of wave, which is a standing wave. Standing wave occurs when harmonics occur, when there's a back and forth motion, typically when a transverse wave hits or a sound wave hits and then reverberates back. When it does that, it will flip. And when we do a lab, you'll see this. And when we do constructive and destructive interference, it will flip in an alternate direction. So, for example, the wave may be traveling in like this, following my cursor. Once it hits, it gets actually flipped upside down and flows backwards in the opposite direction. What that does is it forms these antinodes. Antinodes are these humps. Okay, easiest way to say it. There are these humps when a sound and when harmonics are created. These spots right here where the waves meet are called antinodes. So when we talk about a standing wave with one harmonic, what we're going to look for is one hump or one antinode. If I told you to draw a standing wave with two harmonics, you would draw a wave with two antinodes or two humps. If I asked you to identify a standing wave with three harmonics, you'd choose this one because you count 1, 2, 3. Here's a standing wave with four harmonics, 1, 2, 3, 4, and you get the drift for 5. This is the end of the lecture. If you have any questions with any of this, please contact me. Otherwise, have a great rest of your day.